Hello everyone, I'm Wei Bai from Hong Kong University of Science and Technology. And today I'm going to talk about our work, Information-Agnostic Flow Scheduling for Commodity Data Centers. And this is a joint work with Chen, my advisor, Professor Chen, and Wang from Sing Group, Hong Kong University of Science and Technology, and Professor Dongsu from KAIST, and Professor Chen Tian from Nanjing University. First of all, I want to talk about the background of this work. The context of this work is data center. So as we all know that data centers are very important infrastructure for today's cloud computing. So there are many applications running the data centers, such as the web search, high-performance computing, database, and cache. Okay, for this application, to serve a user request, they will generate a lot of short request and response messages during the data center, across the data center networks. This application, they all desire ultra-low latency for this short message, because the completion time of this short message will directly determine the user experience. Okay? In this way, one of the most important design goals of the data center transport is to minimize flow completion time, especially for these short flows. So to address this challenge, there are many flow scheduling proposals in recent years, such as the PDQ, pFabric, and PIAS. And these solutions, they can provide very good or even near optimal performance. However, we found that all of them assume prior knowledge of flow size information to approximate ideal shortage of first scheduling with customized network elements. For example, the pFabric, it introduced non-trivial modification to switch hardware. And PIAS, it requires a separate and very complex control plane for arbitration. We know that the assumption of prior knowledge of flow size information does not hold for many cases. For example, for the database query and response, the response data is transferred as soon as it is generated without buffering. So we can now know the total size of the response data beforehand. And in addition to this, the customized network elements make this solution very hard to deploy in production data centers. Here, we take one step back and ask a fundamental question. Without prior knowledge of flow size information, how to minimize FCT in commodity data centers? Based on this question, we summarize the following three concrete design goals. The first design goal is information-agnostic. As I have mentioned, the assumption of flow size available from application does not hold for many cases. Therefore, we should not make such assumption. The second design goal is FCT minimization. We should enforce a scheduling policy to minimize average and tail FCT for short flows while not adversely affecting the FCT of large flows. The third design goal is readily deployable. We should avoid introducing change to any element in the data center networks. Our solution fully utilize the functionalities provided by existing commodity switch hardware and be compatible with legacy TCP/IP stacks. So based on above analysis, we give our answer to this question. That is PIAS. Now we talk about the PIAS design. So the design rationale of the PIAS is very simple. PIAS perform multi-level feedback queue to emulate shortage of first without prior knowledge of flow size information. So what is multi-level feedback queue? I use this figure to show this. So as we can see from this figure, we have K priorities. Know that priority 1 is the highest and K is the lowest. So during a flow's lifetime, its priority is gradually demoted from the highest one to the lower ones. Okay, for example, for this flow, okay, the first packet is assigned to the priority 1. Okay. And for the second priority, it's assigned to the priority 2. And for the third packet, its priority may be further reduced. And for the last packet, if this flow is large enough, it will be assigned to the lowest priority. So we found that the multi-level feedback queue is quite simple. But why this works? Why this can be used to minimize average flow completion time in data centers? Here I use a very toy example to show this, and later I will explain the reason behind this. And in this topology, there are 3 servers connected under the same switch. and the left to a sender and the right one in the receiver. So congestion happens here in this egress port. And on switch, we use a 4-level feedback queue to do the scheduling. Okay. Now, okay, we have 2 flows, and flow 1 with 10 packets, and flow 2 with 2 packets arrives. So flow 1 and flow 2 transmit simultaneously. Okay, initially, both of the flows are assigned to the highest priority, so they fairly share the link capacity. Okay, here, now, flow 2 is finished in the highest priority, while flow 1 is demoted to the second priority after sending these 2 packets. Okay, so here, a new flow, say flow 3, comes. It is also a small flow. It has 2 packets. So flow 3 and flow 1 transmit simultaneously. Note that the flow 1 has been demoted to the second priority, but flow 3 is a new flow. It is in the highest priority. So flow 3 is prioritized over the flow 1. Okay, so now flow 3 is finished, while flow 1 is demoted to priority 3 based on the multi-level feedback queue. Okay. Now, a new flow, say flow 4 with 2 packets arrives. So flow 4 and flow 1 transmit simultaneously. The flow 4 is in the highest priority. Flow 1 is the third priority. So flow 4 is prioritized over the flow 1. Okay. So flow 4 now flow 4 is finished. And okay, the flow 1 is demoted to the lowest priority. And eventually, it is finished in the lowest priority. So during this example, we found that even without prior knowledge of flow set information, the peers makes very similar decision as started out first, except for the contention between the flow 1 and the flow 2 at the beginning. So the reason is that with peers, short flows are more likely to be finished in the higher priority queues, while the large flows are more likely to be finished in the lower priority queues. So short flows are prioritized over the large flows in general. But there is still a very practical issue. Note that the multi-level feedback queue is not directly supported by commodity switch because it's very hard to track per flow state on switch. So to solve this problem, our solution is to decouple multi-level feedback queue. On switch, we only enable the strict party queuing. This is a basic function provided by most commodity switch. And at end host, we implement a packet tagging module. Okay, the logic of this module is quite simple. I have k priorities, and correspondingly, I have the k-1 demotion threshold. The threshold to demote priority from pj-1 to pj is alpha j-1. So for the module, I just track the per flow state, and I compare the byte sent information for flow against predefined demotion threshold. If I find that for flow is byte sent information is exactly larger than alpha j-1, that means the next packet should be assigned to priority pj. So we can see, okay, for this packet, if you mark with 1, you will go to the first priority queue on network switch. For this packet, if you mark with 2, you will go to the second priority on switch. A very interesting part of peers is its demotion threshold. Intuitively, we know that this demotion threshold, they can directly determine the performance of the peers. Okay? So how to determine demotion thresholds? We built a very simple queuing theory model to analyze, and we found that the ideal threshold in theory depends on both flow size distribution and traffic load. So we can calculate threshold by solving an FCT minimization problem based on the traffic information we collect from the inter data center. But that is not the end. We know that in a data center, the traffic is highly dynamic. That means the traffic is always varying across and time space. For the same link, it may have different flow size distribution in different times. And at the same time, different links may also have different flow size distribution. The traffic variation will cause a mismatch between the demotion threshold and traffic. Even though we can periodically update the demotion threshold based on the new traffic information we collect from the inter data center, but that is far from enough. How can we keep peers good performance in highly dynamic data centers? Okay. Before we come up with a solution, we should fully understand the impact of the mismatch. Okay, here's a 2 example. In this network, okay, there are 2 party queues. That means you only need to determine 1 demotion threshold. And there are 2 types of flows. The large flows, say 10 megabytes, and short flows, say 20 kilobytes. So intuitively, if we want to achieve ideal flow completion time, for the short flows 20 kilobytes, the demotion threshold should be set to 20 kilobytes. In this way, all the packets of short flow will be exactly finished in the high priority queues, but almost all the packets of large flow will be finished in the low priority queue. However, if we set a too small threshold, say 10 kilobytes, that means the last few packets of short flows will be prematurely put into low priority queues, and they may experience very large queue latency due to the impact of the large flows. Similarly, if we set a too large demotion threshold, that means many packets of the large flows will overstay in the high priority queue. This will also hurt the latency of the short flows. We found that no matter we set a too small or too large demotion threshold, the result is the packets of the short flows and large flows coexist in the same queue. Note that the number of priority queue in data center switch is very limited. So we can now use more queues to further segregate this traffic. So our intuitive solution is to use ECN to keep low buffer occupation. Even though we can now totally avoid this impact, but we can minimize this impact. Okay? When the threshold is too small, if we enable ECN, we can control the buffer occupation in the low priority queues. If the threshold is too large, if we enable ECN, so we can ensure the packets of the short flows can experience moderate latency in the high priority queues. So here, I summarize the PIAS design in one slide. Actually, PIAS is quite simple. It only has 3 components. The first component is PIAS packet tagging module. It is responsible for maintaining per flow state and mark packets with priority. The second component is PIAS switch. I just enable 2 basic functionalities of commodity switch, strict priority queuing and ECN. The third component is rate control. We employ DC-TCP as the transport layer protocol to react to ECN. We found that all of these 3 components, they are very easy to implement or configure in production data center. Okay, now here is the Testbed Experiments. So we have already implemented a PIAS prototype, and it is open source. You can get our code from this website. And note that we have implemented the packet tagging module as a Linux kernel module. That means you can install this module or remove this module during the running time of the system. You don't need to modify and recompile the kernel. And for the testbed, we use 16 servers and a gigabit switch. And for the benchmark traffic, we use web search workload from the DCTP paper, data mining workload from VL2 paper, as well as memcached application. So these 2 figures show the average flow completion time of the short flows in our testbed. Note that in our testbed, we only evaluate PIAS, DC-TCP, and TCP. And for the information-aware solution, because they leverage some customized network elements, so it's very hard for us to implement this in our testbed. We found that compared to the DC-TCP, PIAS can achieve 47% lower FCT in the web search workload and 35% lower FCT in the data mining workload. The reason is the DC-TCP want to achieve low latency but control the buffer occupancy. But if DC-TCP wants to fully utilize the link capacity, it still needs to maintain a moderate buffer occupation. So there's always a trade-off between the latency and throughput for DC-TCP. But with PIAS, the packets of short flows, they are likely to be finished in the higher priority queues. That means they can experience much fewer latency or even 0 queuing delay. We also conduct extensive NS2 simulation. For the topology, we use the span leaf with 10G and 40G links. And similar as the testbed experiment, we also use web search and data mining workload. And we compare the PIAS against 2 information-agnostic schemes, DC-TCP and L2-DCT. And for the information-aware schemes, we choose pFabric, because in our setup, pFabric can achieve near optimal performance. And these 2 figures show the overall average completion time achieved by DC-TCP, L2-DCT, and PIAS. We found that PIAS outperforms both DC-TCP and L2-DCT. The reason is the DC-TCP, it is still a fair sharing scheme. On the basis of DC-TCP, L2-DCT acts as a byte sent information to the window adjustment function of the DC-TCP. But it is still distributed and host-based reactive rate control. But for PIAS, we leverage priority queues on commodity switch to enforce multi-level feedback queue scheduling. It is more efficient. And these two figures show the average flow completion time of the short flows in our NS2 simulation. We found that compared to DC TCP and L2 DCP, our solution can achieve 30% to 50% improvement, and this result confirm our testbed experiment results. Okay, finally, I compare the PIAS against pFabric. Note that pFabric is the information-aware clean slate design. It not only assumes prior knowledge of flow size information available from application, but also introduce non-trivial modification to switch hardware. For PIAS, we don't make such assumption, and we just use commodity switch. Even those, PIAS can achieve comparable performance as pFabric in short flows, especially in the data mining workload. Here, PIAS only has a 4.9% performance gap to pFabric. So here, we conclude this paper. We think that PIAS is a practical and effective solution. First of all, it is information-agnostic. It does not assume prior knowledge of flow size information available from application. Secondly, it infers multi-level feedback queue scheduling to achieve FCT minimization. And thirdly, it is readily deployable in production data center because we just use commodity switch and legacy TCP IP stacks. That's all of my presentation. Thank you very much.
Very interesting work. Mo from UIUC, and I have a question about a quick question about like what is the impact of the number of queues in the hardware switch have on PIAS, and like what is the number of queues you used in the evaluation here?
Okay, thanks for your question. So in our experiment, by default, we used 8 priority queues. And we found that compared with 2 queues, the first queue can introduce very obvious performance improvement. But the performance from 4 queue to 8 queue is very limited.
I see.
Okay, thank you.
Thanks.
Hi, Eric Rosner, IBM Research. You showed a lot of performance for the mice flow completion time, but what happens with the elephant flow throughputs?
You mean the flow completion time of the large flows?
Yeah, since you're sticking.
Yeah, we have. You can see the more data in our paper, and we found that compared to the DCTP, we achieve higher IFCT for the large flows, but we fully utilize the link capacity.
Okay. When you say higher, how much higher?
It's better to see my paper. There are many figures here.
No worries, I'll take a look. Thanks.
Hi. The question I'm asking maybe is like a problem for all systems that try to do a shortage of first, but I'll just say it. So let's say I have a threshold of 10K for the flow to be demoted to the second priority queue, right?
Yeah.
And then all of my flows are 20 kilobytes, all of them. And I'm getting many of them per second, okay? So what's gonna happen is, a flow sends 10 kilobytes, then gets demoted, then another flow comes and sends 10 kilobytes, and the number of flows I have in my system basically explodes exponentially. If I have enough new flow arrivals per second, none of the flows will ever finish.
You mean the starvation problem, right?
It's not really a starvation problem. I mean, starvation when you say, of course, when you have shortest job first, you could think that you could starve longer traffic, right?
Yeah.
Here, all the flows are the same size, okay? Yeah. But you still get this weird issue. It's like congestion collapse, more or less, because the number of connections in your network will
So you mean it's a uniform distribution, right?
Yeah. It's exactly the same size. So all flows are 20 kilobytes, but your threshold is 10 kilobytes.
That means
and they're coming at a very fast rate.
So it means all the flows are finished in the high priority queue, right?
No, because your threshold demotes them after the first 10 kilobytes, yeah?
It's 10, so you mean the threshold is 10 kilobytes,
yeah.
And all the flows, they are exactly 10 kilobytes?
20.
Is it 20?
Yeah.
Yeah. I guess that our solution performed very well in the long tail distribution, but in some, the uniform distribution, I think maybe our solution cannot perform very well.
So I'm wondering if that's a problem with all shortage of first or just your one. Because when you gave the simple example in the beginning, I was like, okay, what happens if you get always a new packet in the first queue? But I don't know if it's the same true for pFabric or not. Maybe we can take it offline. Thank you.
Okay.
Yeah, Chen from Xi'an Jiaotong University.
Okay.
You just mentioned that you use ECN to control the queue length to reduce the latency, right?
Yeah.
But if the link is not congestion, is not in a congestion state, will this solution just reduce the link utilization?
Actually, if you set a moderate ECN marking threshold, I don't think ECN will hurt the link utilization. You can see the recommendation value for ECN in the DCTCP paper. We also use the same setup as the DCTCP.
Okay, thank you.